3.2 logarithmic functions. I'm sure you've seen this before in algebra. What are logs? The main definition of logs, to recall, if we have y equals log x base a, this is equivalent to say a to the y equals x. A to the y equals x. Right? A to the y equals x. So if we have log m base a equals n, this is equivalent to write it as a to the n equals m. So the left hand side is called logarithmic form, the right hand side exponential form. Next one, log 100 base 10 equals 2. So rewrite that in exponential form. And then we're going to use that to solve some equations. Say log 8 base 2 equals x. So here, this is 10 square is 100. Like 10 to the second power is 100. That's the main definition. That's how you convert things from logs to exponential and vice versa. Now, what about the next one, the equation here? How do you solve the equation? We do follow that definition. 2 to the x equals 8. So what can x be? What is the x value that would make this 8? What is it? 3. Yes, 3. Because 2 to the third is 8. Try the next two.
Number 2.
So number 2, we have x squared 16. So what is x? 4. It can be negative. The base can be negative. 11 to the 0 is x. So 1 is x. 25 to the 1/2 is x. But 25 to 1/2, that's the square root. So 5 equals x. That's how we apply the definition of logs. Now, on the top of this, we need to learn how to graph log functions as we did in exponentials. The main function, let's take an example, log x base 2. So to do that, the easiest way is to convert this into exponential form, which is 2 to the y equals x. 2 to the y equals x. So then what do we do after that? We can create a t-chart, x, y. And how do we solve this? We get x values. In a smart way, I'm going to pick 2 to the 0. Because if this is 2 to the 0, then y is 0. Pick 2 to the 1, y is 1. 2 square, y is 2. 2 to the negative 1, y negative 1. So remember, this is simply 2, this is 4, this is 1/2, this is 1. So the points are 1, 0, 2, 1, 4, 2, 1/2, negative 1. You get 4 points. We're going to plot them on the graph and connect them. One, 0, 2, 1, 1/2, negative 1. So it's going up. Domain here is x bigger than 0. And range is all real numbers. Now, logarithmic functions, they have properties. They have their own properties. And there are a lot of them. We're going to introduce them here. For positive numbers, m, n, a, and b. b is not 1. First property says log mn base a. This equals log m base a plus log n base a. So the product becomes addition to log m over n base a is log m base a minus log n base a. The next property, log n to the k power base a. You can bring the k down. Log n base a. Next one, log a with the same base a, it's 1. Log 1 base a is 0. And the last one we call change of base formula. If you have log m base a, you like to change to base b, so you do log the top base b, log the bottom base b. This is called change of base. Example to apply the properties. So for log 10, you need to look at what is given. They have a 2 and 5. So 10 can be rewritten as 2 times 5. So this is log 2 base a plus log 5 base a. Log 2 is 0.41. Log 5 0.72. 3, 11, 1.13. Another one I want you to try, 5 over 2 base a. It's log the top minus log the bottom. It should be base 10 here, not just base a. So log 5 is given as 0.72. The other one is 0.41. And what does that give us? 0.31. For the next one, it's log 1 base a minus log 8 base a. Log 1 is 0. 8 is 2 to the third. Bring the 3 down. Log 2 base a is given. (0.41). So that gives us negative 1.23. Log 2a base a. We can do multiplication here. Log 2 base a plus log a base a. Log 2 base a is given. 0.41, and log a base a by the one of the properties is 1. So that gives us 1.41. So other things to learn, always for log x base 10 automatically means log x. So log x means base 10. And we have a special kind of log we have. If we take log x base e is the exponential number, 2.7 from the previous section. If we have it this way, log x base e, then this is the same as natural log of x. Again, e is about 2.7. It's like the pi, it goes forever decimal wise, but we just use 2.7 as the same way we use 3.14. Now this function, the natural log, has properties which are similar to the log functions, which says log x times y, it's or natural log is natural log of x plus natural log of y. 2. Natural log of x over y is natural log of x minus natural log of y. 3. Natural log of 1 is 0. And natural log of e, because the same base, it's 1. Natural log of x to the k, you can bring the k down. Same properties as in the log function. So if you have log a base b, you can use natural log of a over natural log of b, change of base formula. And to apply them, we may look at an example. Determine the natural log of 10. So natural log of 10 is natural log of 2 times 5, natural log of 2 plus natural log of 5. Natural log of 2 is 0.6931 and 1.6094. And what we can do here is add them up, which gives us 2.3025. Another example, natural log of 5e cubed. What do we do for this one? We can rewrite it as natural log of 5 plus natural log of e cubed. Natural log of 5 is given 1.6094, and here bring the 3 down, natural log of e. Natural log of e is 1 by the properties, so we get 4.6094. Next one, how are we going to solve this equation? The problem with this equation is having t on the top. Makes it more difficult. So to be able to solve such an equation, what we are going to do is we are going to do natural log both sides, because natural log has the property that allows us to bring the t down. So it becomes t natural log of e equals natural log of 5. But natural log of e is 1. So you get t equals natural log of 5. So t is about 1.6094. Next one. Again, we do natural log both sides. Bring that down. Natural log of e is 1. Then t would be natural log of 8 over 0.02. And if you put that into the calculator, that gives 103.97. And I highly recommend, if you have a calculator, do it now. Make sure you know how to use it. So far, all we have done is algebra. The calculus part is going to start now, is how to find derivatives of natural log of any function. So if I call that function u, natural log of u, then y prime, its derivative, it's u prime over u, no more natural log, u prime over u. So if we have y equals natural log of x, we need to find its derivative. Same thing for this one. So for the first one, it says you find the derivative of this, which is 1 over itself. Done for this. Try the rest. So y prime is 2x over itself. Y prime is 6x plus 6 over itself. Y prime is 11 over itself. They cancel. Next two examples. For this one, if you tried 5, derivative of this is simply 2 over 2x. No need for the absolute value. So that would give us 5 over x. For the next one, y prime is the derivative of the top over itself. We learned the derivative of the exponential function is e to the x. Derivative of 10 is 0 over itself. Then we have an application here for logs. If you can write it down. For part A, they want us n evaluated at 1000, which is 1000 plus 200 natural log of 1000, which is 2381 units. So a calculator is needed. Part B, find n prime. So n prime of A, let's see. The 1000 is 0, 200 times the derivative of natural log of A is 1 over A. So it's 200 over A. And then they want us to evaluate that at 10. So 200 over 10. It becomes 20. That's for part B. Part C, find the max and minimum values of n, if they exist. So again, n of A to recall it was 1000 plus 200 natural log of A, and it was given A bigger than or equal to 1. So if you take A equals 1, that's the smallest value you can pick. We know then n of 1 would give us 1000 plus 200 natural log of 1, which natural log of 1 is 0, so the answer is 1000 units. That's the minimum you can have. And guess what? If you remember the graph of natural log, it goes like this at the beginning of the lesson, like that. It doesn't stop anywhere, so it keeps going forever. So there's no maximum. Part D, we already found n prime of A. It was 200 over A. They want us to find the limit of n prime of A as A goes to infinity. This equals limit as A goes to infinity. N prime of A is 200 over A. So this goes to 200 over infinity. That's 0. A number over infinity is always 0.